Let's do another specific heat calculation, this time comparing the heating of copper to aluminum, so two different substances in the same problem. So we're given that equal masses of copper and aluminum wire receive heat energy at the same rate over the same amount of time. So here's our copper wire, here's our aluminum wire. I picked those two because they're the two most common elements used for wiring in a house, but honestly it doesn't matter what we picked. We just want to do a comparison between two different substances. So both of them are heated. And the important assumption here is that whatever Q dot is, it's constant and it's for the same amount of time for both substances. So we turned the heat on, now let's turn the heat off. Okay, and experimentally, let's say that we determine that the change in temperature of the aluminum over to the right is 10 Kelvin. So whatever the heat transfer was, it generated a temperature difference of 10 Kelvin in the aluminum. We want to know what the change in the copper's temperature is, and we can calculate that now if we know the specific heats for both substances. We also know that wire is solid, so it's incompressible. That will help. We have to look up the specific heats, so in this case I'm just dropping the constant pressure or constant volume subscript. We already saw in the last tutorial that once you're dealing with an incompressible substance, the specific heats end up being the same anyway. So the subscripts here are going to indicate the material. This is the specific heat of aluminum is 0.903 kilojoules per kilogram Kelvin, and the one for copper is 0.385, same units. Okay, so let's get started. As always, with these sorts of problems, we'll start with conservation of energy and then simplify things considerably because delta KE, delta PE, and W are all zero, so we're back to delta U equals Q. Now an important detail is that if they have the same heat transfer rate and the same amount of time, QC must equal QA, right? You must have transferred the same amount of heat energy to both the copper and aluminum wires, so we can immediately conclude that the two changes in internal energy must be equal to one another. Delta UC equals delta UA. We also know generally how to relate delta U to its specific internal energy through delta U equals m delta little u. So if that's true, we have the same masses of copper and aluminum, therefore the changes in specific internal energy must also be equal for the two substances. So let's move that up. Alright, what to do next? Well, here is where you refer back to your lecture notes. For an incompressible substance, you can take this shortcut over to the left, that delta U equals C delta T. So if we put subscripts on that expression, we now see that C sub C, which I realize is awkward, that's the specific heat for copper, times delta T sub C must equal C sub A times delta T sub A. Alright, let's rearrange this for the change in copper's temperature, delta T sub C. We do that, and now we can just put in values for both the specific heats and delta TA. Alright, we do that, and we calculate that delta T sub C equals 23.5 Kelvin. Interesting. So you change aluminum by 10 Kelvin, add the same amount of heat to copper, it changes it by 23.5 Kelvin. That tells you how specific heat usually works for an incompressible substance. Now remember, if it's not incompressible, you can't use that shortcut on the left. You may be doing other things to the internal energy, but for an incompressible substance, there's a direct proportion between the change in internal energy and the change in temperature, and that tells you how the specific heat ends up affecting the change in temperature.